Okay, we've got a 6 kilogram mass and a 5 kilogram mass suspended by a rope over a pulley. We assume the pulley has a negligible diameter, although that's maybe a little unrealistic because the rope has to be fairly thick because it has a mass of 100 grams per meter. So this is not the Atwood machine program with a light string. It's more complicated than that, and it's actually a situation that you aren't in a position to completely solve, but we want to be able to set it up. So I'm going to do what we did in class, and then I'm probably going to do just a little extra. Okay, well, there's 1 meter of rope on this side above the 6 kilogram mass, and there's 19 meters of rope on the other side. So what's the net force in this system? Well, we have 60 newtons acting downward here. We have 1 newton acting downward here because 1 meter of rope has a mass of 100 grams, which has a weight that we round off. It's 0.98 newtons. We're going to call it 1 newton. Then we have a 5 kilogram mass over here with 19 meters of rope, and each meter has a weight of a newton since it has a mass of 100 grams, okay, 0.1 kilogram. And again, we're rounding that 0.9 newtons per meter up to 1 newton per meter just to give an approximation and not have to worry about all the significant figures. And of course we have 50 newtons acting downward on the 5 kilograms. Once more, assuming acceleration of gravity is 10 meters per second squared instead of 9.8 or 9.81. Net force then is what? Remember, and we talked about it in the preceding class, that the default positive direction for rotation is counterclockwise. And this system is tending to, in a sense, rotate. Okay? We can't say that the positive direction is downward because if one of these is moving downward, the other's moving upward. So what's the direction? If this one's moving downward and this one's moving upward, you're kind of at a loss. So we take the positive direction in this case to be the default counterclockwise. And if you wanted it to be clockwise, you could state that and then use that. It'd be perfectly acceptable. Maybe a little bit of a grammatic faux pas, but nothing serious. So we have negative 61 newtons here because 61 newtons, not because it's acting downward, because it's rotating the system counterclockwise. So we have a negative 61 newtons and a positive 15 and 19 makes 69 newtons for a net force of plus 8 newtons. Again, meaning a net force of 8 newtons that tends to accelerate this mass in the counterclockwise direction so that the system moves in a counterclockwise direction. Now, how do we calculate the acceleration of the system? Well, we ask how much mass is being accelerated, and we divide the net force by that. How much mass is being accelerated here? Well, unlike what I've seen, somebody wants to take the difference of these two masses. Well, it's not the difference of the masses that's being accelerated, is it? It's all the mass that's being accelerated. So all 6 kilograms and all 5 kilograms and all 2 kilograms of rope are being accelerated. So the acceleration is 8 newtons over all that mass. And we get 0.62 meters per second squared. Now that's the initial acceleration. The acceleration doesn't remain constant. Why not? Well, let's think about it. At the 3 meter position, well, you now have a couple of extra meters of rope here, so you got a couple of extra newtons on this side. And you got a couple of meters less on this side, so you got a couple of newtons less on this force. So a couple of newtons more, a couple of newtons less, couple of newtons more on the negative side, couple of newtons less on the positive side means you got 4 newtons less force. And you can write that out formally. You got the negative 60 newtons from this. Now you have negative 3 newtons from the rope on this side, from the 3 meters of rope. And then you have a plus 50 newtons on this side and a plus 17 newtons because you now only have 17 meters of rope. So your net force is now only 4 newtons. Okay, well, we only allowed a couple of extra meters of rope here, and we all of a sudden lost 4 newtons of force, and we're only talking about a force that was originally 8 newtons. We lose another 4 newtons, well, where are we going to be? Well, let's think about it, but at the 10 meter position, let's just take the 10 meter position. What's the net force? Negative 60 newtons here, plus 50 newtons here. The weights are still on their respective sides. But now we've got 10 meters of rope on this side that's pulling in the negative direction with 10 newtons of force, or being pulled in this direction with negative 10 newtons of force. And 10 meters on the other side that's pulling in the positive direction, that's being pulled in the direction that will move the system, or accelerate the system counterclockwise. Okay, gravity's pulling on it with that force. So now these two balance out, and we end up with negative 10 newtons. Well, we had 8 newtons here, 4 newtons here, when we went at the point when the thing had declined to the 10 meter position. And now, to the 3 meter position, we'd have the 4 newtons. And by the time we decline to the 10 meter position, if we ever actually get there, depending what our initial velocity might be, okay, we're being pulled in this direction, and we're speeding up in this direction. Okay? Whereas before, we were being sped up in the counterclockwise direction. So we've reversed the direction of our net force, which means that if this thing does make it to a certain position, the net force is going to go negative, and it's going to continue to speed up now as this side declines. So depending on what initial velocity we give it, because in this position, if it's at rest, it's not going to move because its acceleration is in the direction of counterclockwise, and it's already resting on the floor. If we beat on it, give it an initial velocity, it'll go down a little bit, then it'll accelerate back this way. But if we hit it and get it moving fast enough, it'll make it to the position where the net force becomes negative, and then it starts speeding up as it goes down. So it slows down, but if it goes far enough, then it starts speeding up again. That's kind of interesting behavior. So we ask now, where is it? How far does it have to get in order to keep going? In order for this thing to actually make it to the floor? Well, it has to get to position X such that the acceleration is 0. If it gets to that position and it's still moving, then it's going to go past that position, and the acceleration is going to become negative, and it's going to start speeding up, and then this thing will reach the floor. Okay, when does that happen? Well, net force is negative 60 newtons, here, and a plus 50 newtons here. Those weights masses are still on the same side. Each is on the side it started at. On this side, we've got 1 newton per meter of rope. Again, meter of rope, 100 grams. Gravity pulls on it with 1 newton of force. So we have 1 newton per meter times X pulling on this side, so that's going to be negative. And then 1 newton per meter on this side multiplied by whatever amount of rope we don't have on this side. Well, if what we have on this side is length X, what we have on this side is going to be 20 meters minus X, because there is a total of 20 meters of rope here. Again, we're assuming a negligible pulley diameter. And we can solve that for X and find out just how far this thing has to go before it will continue. So it's kind of an interesting problem, and at the next chapter we're going to be talking about energy. And when we talk about energy, we can bypass some of the details of the motion and actually learn more about this system without having to resort to differential equations. I'm going to digress in a short, hopefully short video in a minute, and just tell you, how you could write out, use your calculus, what you know about your calculus, to write out the differential equation for the motion of this system. You won't know how to solve it, and it's not all that easy to solve, even if you do know differential equations. But I'm going to write it out and do just a brief discussion just to give you something to be excited about for next semester.